All right. Hi, everybody. Thanks for coming. Today we're going to do a super deep dive into DNS, the domain name system, which is one of the foundational protocols of the internet. DNS is used every day, trillions and trillions and trillions of times. God, I wouldn't even know how to estimate how many DNS queries are floating out there. We certainly get a lot here at Amazon Web Services, and it's something I've worked on a fair bit. I had a hand in writing code that is in NSD, and I certainly am very familiar with Bind 9 and stuff that's in there, and I also helped write the DNS software that we use here at Amazon, and I was lead engineer for Amazon Route 53 for a while. So if I get any details wrong, which I probably will, it is very much on me, and definitely embarrass me and call it out. DNS is a very, very big, broad topic. All right, so where to begin? We're gonna cover all sorts of things. We're gonna go how DNS works on the wire. We're gonna go how DNS queries are resolved through resolvers and caches and forwarders, and what a stub resolver is. We might even have to get into how PathMDU discovery works a bit to kind of cover why DNS uses both UDP and TCP. We're going to get into crazy things like Q tuples and Q data. We're going to leave this understanding what glue records are and how those work. There's going to be a lot to take in, but I'm going to try to go starting with the basics, and we'll work our way up, and hopefully we'll all be able to track. And feel free to drop questions along the way, or if something isn't unclear, and I'll try to catch it in a moment, and if not, we're going to scan all the questions at the end. All right, so I'm going to switch to my document view. So let's start with, we all know probably what a DNS name looks like, right? So I'm going to use a pretty straightforward example here. www.amazon.com, right? So that's a domain name, that whole thing. And you type that into your web browser, something happens, and then somehow your web browser can then talk to Amazon.com, right? And what's happening, right, is your web browser and other software on your machine is taking that domain name and turning it into an IP address, right? That's what DNS does. That's its biggest, most important job, is taking domain names and turning them into IP addresses. Because when your web browser actually needs to talk to a web server, which is where it gets its content from, it does that, needs to know the IP address. It needs to know what to talk to, right? But humans can't remember IP addresses. There's 4 billion IPv4 addresses, and there's 2 to the 128 potential IPv6 addresses. They're not easy things to remember. I've got a cache of IPs that are just locked into my brain from systems I've administered over the years, but it's a pretty small list, and certainly wouldn't be able to remember what the IP is for Amazon.com. And those IPs change over time too, right? Sometimes the folks that are running a website have to change the data center that your connection is going to, or they have to spread load across multiple data centers and so on, and DNS is often used for that too. So sometimes, these domain names don't even translate to just one IP address. Sometimes they translate to many IP addresses, and there's a few different ways to do that, and we'll cover that too. But that's the most important example of what it does. So DNS takes a name and turns it into an IP. So I'm going to use this as an example IP address, or if we're in IPv6, just to be fair, we're going to do something like that, right? So that's the biggest, most important job. All right, so let's kind of familiarize ourselves with the kind of hierarchy of things that are actually doing the DNS request, that are doing the DNS work, right? So we're going to start with your browser. So this is my, crude picture of a browser where you actually type the domain name in, right? And that's going to be the first place that does any DNS processing. And modern browsers often actually have relatively sophisticated DNS stacks built in. They no longer just outsource this to the underlying operating system. Sometimes a web browser can have a full-blown, DNS implementation of its own, and it can keep a cache, right? So it can go, well, the first time you go to www.amazon.com, it doesn't know the answer, and it has to do the full DNS processing that we're going to walk through. But after that, it can cache that answer for a while, right? So these answers are cacheable, and that's an important concept, and we'll see how that fits in later. And it can keep a cache. So when you ask your web browser, if it happens to know the answer already, if it's in its cache, it doesn't really need to do anything. Knows the IP, can just reuse it, right? But if it doesn't, it's got to go resolve it. And there's so either the browser will do this itself, or the operating system that you're running on. So here's my picture of an operating system, because I'm on a Mac, so I'm just gonna say it looks like this with a little bar down here. I haven't used Windows in a long time. I can't remember if the bar's at the bottom or the top anymore. But either your browser or the operating system on its behalf will typically act as what's called a stub resolver, right? So that stub resolver is just a piece of software that is responsible for kind of initiating a DNS query and saying, I really want to resolve www.amazon.com into an IP. I need to know it. Please do this for me, right? And a stub resolver doesn't really do much more than that. Just asks simple questions and gets back simple answers, right? And it's asking that question to what's called a recursive resolver. Typically, there can be things like DNS forwarders in here, right, where you might have a machine that understands DNS, doesn't really do anything with it, just forwards it to a recursive resolver. But we're going to kind of ignore that for now. That's just like a proxy for DNS, not a very important detail. But typically, it'll go to what's called a recursive resolver. And a recursive resolver is what does the bulk of the work. It's what's really going to take the name of the query, www.amazon.com, and go through quite a lot of steps to figure out what the IP should be, and then give you that answer back. And we'll go through those steps and how those work. But this is where that work is happening. Now, traditional internet architectures, your ISP would run the recursive resolver, or maybe your internet gateway device, like your some home routers have recursive resolvers built in, though it's more typical that they're just dumb DNS forwarders. But most ISPs do run recursive resolvers. Or if you work at a company, like the corporate internet people probably run some recursive resolvers somewhere. Windows Active Directory can be a recursive resolver, really common in enterprise situations. Or people run Bind9 or whatever they want. On Linux operating systems and servers, things can get a little bit more complicated in here, because maybe they're not just running a stub resolver, but they're running something that's a bit more heavyweight than a stub resolver, something like LWResD and so on, but that's another detail I'm just going to mention and acknowledge the existence of, but not get into too much depth. So the recursive resolver, right, that's doing the main work. It's gonna take the query and turn it into an answer. And for the most part, the way it's doing that is it's talking to authoritative name servers, right? These are all forms of name servers, but this one is not a resolver. It's authoritative. It knows the answers to things definitively, right? That's why it's called an authoritative. But recursive resolver might have to talk to many different authoritative resolvers to build up your answer. We'll see why. But once it's figured it out, it knows the answer, and it can return it to here, and it can also cache it, right? So then, again, the first time you ask a recursive resolver, hey, what's the IP for Amazon.com? Well, it probably doesn't know, so it has to do all this work to figure that out. But then when it figures it out, it's allowed to cache that answer for a while. So the next time the next time a query comes in, it can just answer it right away, right? And of course, straight away, what that caching means, right, is that DNS is an eventually consistent system, right? And what that means is the people who own the data, who own these answers, like me at Amazon.com, like let's say I run the name servers for Amazon.com, and I go in and I say, okay, well, the IP address for Amazon.com is no longer 192.0.2.1, it's 190.2.2, right? So just go make that change. It can take that change a while to kind of reflect in the system, right? Because of this caching, right? I don't have strong consistency. I don't have like transactions or anything like that. And there really wouldn't be any other way to do this at internet scale. You couldn't possibly have everybody who wants to know the answer for Amazon.com, acquire a lock on my authoritative data store somewhere and block any attempt by me to change it and so on. Like it just wouldn't scale, especially when you consider the world is the size that it is, and there's 400 milliseconds best case between any two sides of the planet and so on. There's certain physical constraints that you just have to live with, right? And so it's an eventually consistent system. If I make a change for what an IP should be, it can take a while to reflect in the system. And this caching, right, it's all moderated by something called a TTL, right, a time to live. So DNS answers, they don't just have this answer in it, like the IP address. They also have a TTL associated with them that says, you're allowed cache this for up to 300 seconds or 5 seconds or 2 days, right? And then everything down the chain can cache that for that long, right? And let's tease that out. So let's get into some real detail there. Let's have this be our first place where we go super, super deep. So firstly, you can have a tier of resolvers. In fact, we already have a tier here, right? Like, so your browser might be the first tier, your operating system might be the second tier, your recursive resolver, then the third tier, and the recursive resolver might point to another recursive resolver because you want a hierarchy of caches. It's a common way to get better cache locality and better cache efficiency. And if they were each just looking at the TTL, and things would break down. So imagine here at the auth name server, imagine I said the TTL for Amazon.com is 300 seconds, right? And okay, so this recursive resolver takes that answer and caches it for 300 seconds. Great. Now imagine we're almost at the 300 seconds. Let's say we're getting to second number 299 of since it cached that record, right? Sorry, I gotta move my camera a little. If this recursive resolver answered the stub resolver and said, here's the answer for Amazon.com, the TTL is 300 seconds, right? Okay, so another 300, but now it would be like, well, we were at second 299, and I've just told this guy he can keep it for another 300 seconds, so actually I'm going to end up keeping it for 599 seconds, right? And then we did the same thing here, where imagine this guy got to second 299 of its clock, and then sent it to this guy, he'd get another 300 seconds, right? So you can see we'd end up, even though everything said the TTL was 300, we'd end up serving an answer here that was 900 seconds stale, right? So that just doesn't work. Like, that's not a good thing. We want to be able to honor the TTLs. So one of the first principles is, right, when a recursive resolver or stub resolver or anything else down the chain answers with its answer, it has to kind of remove any time spent from the TTL, right? So if I ask this recursive resolver, 150 seconds into the cache time, what's the answer? I'm going to get an answer back, and it has to say, okay, here's the answer, but you can only keep this for 150 seconds or less. You can actually lower it if it feels like it, right? And so on. So you get these descending, telescoping kind of TTLs that get smaller as you descend through the tiers of the system. And that's how we can be sure that even this dude at the end isn't going to have cached the record or used the record that's more than 300 seconds stale, because this guy set up here. So I want to bust some myths here straight away. A common thing you will hear people say on the internet is that DNS TTLs are not reliable, and that things can cache TTLs for longer than they should, and so on. And I'm here to tell you, in my experience, that's completely bogus, and that actually low DNS TTLs, for the most part, are respected. There have been some pretty bad bugs in the past. There was a version of Internet Explorer that didn't do great with TTLs, but that's like long gone. There were versions of Java all the way up until Java 7 that essentially never, they would resolve a name and then never check it again. They just had infinite caches. But for the most part, the internet's pretty clear of those things. And my experience of like many times waiting and flipping traffic between Amazon data centers is that using a low TTL on a DNS record is by far the fastest and most reliable way to do it, right? And we see, huge percentages, way over 99% of clients honoring TTLs, when I just go measure it. If I need to move traffic between two data centers, there's pretty much only two games in town. One is DNS, and the other is BGP, or what's called Anycast, where I advertise the same IP address in multiple locations. And in my experience, DNS is faster, and BGP is slower for a few reasons. One is BGP doesn't have this TTL property. It actually has the opposite. So in BGP, if you make a BGP change in one network, it has to spread through every single network, one by one, hop by hop. And so you've got to wait for each of those networks to converge, and it can be many hops deep, and that can take a while. And so you just don't see as rapid a cutover. And then the second thing is or BGP changes tend to be, they can be service interrupting. They generally break connections that were in flight. And so they're not as fun. DNS is cleaner and faster, in my experience. And whenever we're looking at how we want to flip traffic between data centers or regions or availability zones, DNS tends to be our go-to technique, and I'm very happy with it. I prefer it. So we've kind of oriented ourselves a bit here, right? We now know, okay, what DNS is doing, the kind of components that are involved. We've got a Stub Resolver over here on the client side, talks to a Recursive Resolver, does all the work, talks to authoritative name servers that know all the answers, right? So those are the components. Now we're going to orient ourselves in a very different way about internet layering, right? So you probably know that there's layering models for the internet or applications in general, things like the OSI layering model, which is pretty much completely out of date and totally bogus, and who the hell knows what layer 5 and 6 really are, right? And where's TLS in the OSI layering model? Like, it's just totally bogus. So, but we'll take some layers from it, right? So in the typical internet layering model, you've got layer 1, right, which could be Wi-Fi or Ethernet. It's the physical layer, right? So let's just say it's Wi-Fi for me. Could be like 5G. There's all sorts of things it could be. Then layer 2, which is IP, right? And then layer 3, which is, no, I'm getting this wrong. I'm already off. Sorry. IP is layer 3. Let's say this is layer 2, my Wi-Fi or Ethernet. Physical layer is like, what kind of physical medium are we on? Like free air or RF or whatever. But here we're just going to start at layer 2, which I'm going to say here is Wi-Fi Ethernet. Layer 3 is IP. Layer 4 is things like TCP and UDP. There are more than that, but the ones that are interesting for us are TCP and UDP. And then you've got other layers. In a real layering model, I'd have things like SSL and TLS in here, or QUIC, and then I'd have like HTTP and so on above, right? Now, it's pretty clear from our browser example earlier, right? We're going to speak TCP/IP between a web browser and a web server. That's how the HTTP protocol works. But it needed to do a DNS query first, right? So, naively, you might think, well, there must be a DNS layer below IP, right? IP and TCP/IP clearly depends on DNS, right? Okay. But it turns out DNS actually depends on them too. So DNS is actually an application protocol that runs over, TCP/IP and UDP/IP, right? So DNS is actually its own application protocol, right? It's its own layer 7 protocol, and yet it runs over IP, TCP and UDP and IP. So how does that work? Like, that's a circular dependency, right? Like, that doesn't make any sense, right? We have circular dependencies all the time at AWS. It's a thing we have to deal with. Sometimes we've got systems that say run on top of EC2, but then maybe some part of the EC2 system itself uses the thing that is built on top of EC2, right? And we have a technique to resolve this that we call static stability, right? That we think about a lot in our engineering. And it's a principle that says, well, don't have some kind of like hard synchronous dependency on the thing that depends on you. And definitely make sure that in the event of a power event or any networking outage or anything like that, that the whole system recovers on its own without anybody ever having to intervene. And then make sure that you've got, the right state in the right places, cached in the right ways, or kind of like pre-fetched in the right ways more than really cached. That the system is always stable and could always recover. And so it's okay to use something that's on top of you to like make changes and stuff, but not like have a super hard dependency on it. And DNS is an early example of that. DNS has static stability. The way DNS resolves this circular dependency is the DNS system in itself, to kind of bootstrap things, has a hard-coded list of IP addresses that rarely change. And those are an important part of how the system self-bootstraps, and we'll see how that works in a minute, right? So DNS itself is built on top of TCP and UDP, right? And so if we go back to our diagram here, so these days browsers can talk to recursive resolvers over DNS inside SSL and TLS, or even inside HTTP. That's what DNS over TLS is, or DNS over QUIC, or DNS over HTTP. There's a bunch of different ways to do it. There are providers and browsers doing this. It's pretty cool. But I'm not going to get into that too much because it doesn't change the details of how DNS works too much. It just gives you extra privacy between the browser and wherever your recursive resolver is. You still have to trust your recursive resolver. They're still going to see your query. If you're going to pornsite.com and you don't like people to know that, well, you better trust your recursive resolver because they know it. But no one in between can know it because it's encrypted. And that's kind of all that does. DNS over TLS, DNS over QUIC, DNS over HTTPS. But these queries and these answers going back and forth, and these queries and these answers going back and forth, these are all happening over the DNS application protocol, which will use TCP/IP or UDP/IP. All right. So I think the best place to start is to focus on what the recursive resolver is doing, and how it knows what to do. So your browser knows your recursive resolver by IP address and your operating system, right? So when you boot your laptop, say, on a Wi-Fi network, part of what your Wi-Fi router is doing is giving you an IP address for you to use, but it will also tell you what the IP address of your DNS resolver is. That's part of the DHCP protocol, right? And so that's how we bootstrap this part. That's how your browser and OS know your recursive resolver's IP address without depending on DNS. So your ISP and like your home router and so on have just like hard-coded that IP in their configs, and they tell you whenever you like turn on your laptop and join the network, and your mobile provider is doing the same with your phone and so on, right? They're just literally telling you, here's the IP. So that's how that little circular dependency is resolved. The recursive resolver has more going on, right? So when you first bootstrap a recursive resolver, right? Let's say you just fire it up from scratch. It's never been run before. Built into the configuration of a recursive resolver is what's called a root hints file, right? This is a file that is basically a list of a bunch of IPs for what are called the global root name servers. Root, or OOT, right? I have to be careful how I say that. And this list is maintained by Icann on behalf of Icann and kind of like a global world governance body that oversees DNS, right? So when the internet was started, there were a bunch of mostly academic institutions that put up their hands and said, you know, we're going to help this DNS system run. We're going to run a root DNS server. Put us on the list. Here's my IP. We're going to run a DNS service pretty much on a voluntary basis, and it's going to have and here's its IP address. Put me in the list, please, right? And you know, those folks did a decent job, and they kind of just stay in the list, right? Like, and there are ways to join that list. There are governance processes. You know, there's votes at Icann and so on, and ways to get in. But it really doesn't change. It's an extremely stable list. And I mentioned Bgp Anycast earlier, which is just a technique where, you know, two or more places announce the same IP address, and the internet just kind of figures out, well, traffic should go to your closest one. You know, in the early 2000s, these root DNS providers started experimenting with Bgp Anycast and saying, you know, we should use this instead because we can't just keep adding to the list; it'll get too long. So instead, let's just use this Anycast technique so that multiple data centers and multiple locations all over the world can provide the same service. And that's been a big success. That's worked. So now the list really almost never has to change. And what happens instead is that, you know, different providers agree to stand up different root servers, and they just announce it over BGP Anycast, and now we've got a new root server in there, right? And someone just asked, how does resolve.conf work in all this? Well, just to be clear about it, so resolve.conf, so that's a file on your operating system over here on the left side, like on your laptop or desktop or whatever, and it has the IP addresses that came from your Wi-Fi router, the ones that came in over DHCP, and tells you how to find your resolver, right? But your recursive resolver, this guy, does not use resolve.conf. No use for it at all. That dude uses the root hints file. And so the root hints file, right, just has this list of, well, here's the IPs for the global set of root name servers. And it's a hints file, right? So one of the magic pieces of how this bootstraps is actually when you start a recursive resolver, the first thing it does is it tries to ask basically every single one of those name servers, tell me what the current set of roots it really is, right? So as long as one of those IPs in that list is correct, it can bootstrap, right? So even like, let's say there's like 20 IPs in the root hints file, even if 19 of them are out of date and no longer current, the system will still bootstrap, right? Now that's not going to happen. Like in my lifetime, there's been like 2 or 3 additions and removals. Like it's not a rapidly changing set, but the system's very, very resilient. And DNS as a whole is incredibly resilient, although it does have some stupidity built in that I'll probably rant about. But that's a really clever pattern, right? As long as one of those IPs is good, it can just get the latest copy of, okay, tell me what the root name servers are. And when it's doing that, it's making a query for a domain name. It's just asking each of those IPs, hey, tell me what the current data is for the following domain name. And that domain name is dot. Literally just a dot. That is the root zone, dot. And actually, every domain name can have a dot at the end. We leave it out by convention, but like www.amazon.com dot is the same as www.amazon.com, right? We just leave out the dot at the end by convention, but this is that dot. This is the dot right at the end, and it's called the root zone. So zones are an important concept that will hopefully become more clear as we get through this. But it basically asks each of those name servers, tell me what the data is for dot, and one of them or one or more of them will respond and say, okay, here's the data for dot. Here's the current list of IPs, right, that are in the root zone. And then that's what it actually uses from that point on, right? Like whenever it now needs to ask something of the root zone, it uses that fresh copy, not the one that's in the hard-coded hints file, right? We're going to actually do some queries in a terminal, and we'll see this in action. I'm going to walk through every step that it takes to query to resolve www.amazon.com, and so that'll become more clear. What's in the root zone, right? What we call the zone is like you can think of it as a file or a folder or like a collection of names that are all related, right? So but a zone, it's a little bit of a fuzzy concept in DNS, and I'll explain why. But so here's a name, right? This part at the top is a zone, the root zone, right? And there's like one authoritative data set for what is in that root zone. That authoritative data set is controlled by Icann, right? So Icann is the global governance body that oversees what domain names should exist at the very top level, right? So they're in charge of saying com should exist, and here's who should operate com. Or .net should exist, and here's who should operate .net, right? Or whatever, anything you want, .cloud, and here's who should operate .cloud, right? And then typically, so those things that I just walked through, those are called top-level domains. So com is a top-level domain. And those things are also typically zones, their own zones, right? So com is a zone, and one operator, I think VeriSign, has the contract and maintains the com zone, and they're in charge of, deciding what goes into the com zone and what names exist there, right? And we'll get into registrars and registries and so on later, but essentially, they have a definition that says, Amazon.com exists and is currently owned by Amazon, and then they get to delegate ownership of Amazon.com to Amazon's zone, right? And we at Amazon, we can say, well, this is a zone, this part, Amazon.com, or actually this whole, www.amazon.com could be a zone. Where I'm drawing these lines, these things are called zone cuts. It's the little niggly details that don't matter too much, but technically a zone cut can be pretty much anywhere a dot is. And you could have a zone that's got like www.amazon in it, or you could have a zone for Amazon.com that delegates to a zone that just has www in it. That'll become much more clear, I think, when we do a walkthrough, but it's not too important if you can't follow that detail. Let's cover registries and registrars right now. Why not, right? So like I said, I can control the root zone, and they get to decide what goes on inside here, and who has com, who has each country. .uk goes to a certain company that operates it on behalf of the British government. .us goes to a certain company that operates it on behalf of the US government, and so on. But also, people can buy top-level domains. They've got this generic TLD program where people can just, put up enough money and a decent proposal and say, we think this domain should exist. Here's why we think it would be sustainable and not just a flash in the pan. How about you let us try? And Icann can agree or not and give you that top-level domain or not, right? So that's who controls that one. And then typically the TLD owners, right, like, the folks who operate .com, are considered registries, right? They're called registries because they're like a title registry, right? They maintain a list of who owns what. That's their main job. And usually then there's an open market for registrars. So if you want to buy a domain, right, like you want to buy www.amazon.com, though I happen to know it's not available, you go to a registrar, right, and you say, well, I'd like to buy it, and they'll check if it's available. Or maybe somebody else has it and they might be able to handle an auction or a sale between owners or whatever. But, let's say it's available. They use a protocol to talk to the registry, a protocol called EPP, and say, we'd like to buy this domain and it's going to be owned by this person and so on. And then if the registry says, yep, still available, so now it's yours, they have to sell them typically on a first come, first serve basis. Now you have the domain. Or the registry says, yep, that registrar is now like the registrar for that domain, and here's the owner for the domain. That all gets registered in the registry. There's all sorts of data there, like you have to give your address, email addresses, phone numbers, stuff like that, who is contacts, all that kind of stuff. Almost none of which ends up in DNS. A lot of that just stays in the registry. It's available over the whois protocol. But just remember for later, at this point, glue records do get told, from the registrar to the registry. And if you need glue records, and we'll see later why you might need glue records and what the hell they are, this is kind of when that happens, right? But otherwise, we're just kind of managing a big property transaction here. Nothing that's happening when you register or create a domain is involved too much in how it's resolved, right? So that's how registrars and registries exist. All right, so we're going to go now through what we've established. That the recursive name server, when it starts, has this root hints file. It's all it knows when it starts, and we're going to walk through what actually happens when we do a DNS query, right? So there's a few parts that are important to this. So if you've ever seen a DNS record in a tool like Dig, right? You've probably seen something like this, right? Probably seen like a name on the left-hand side, and then a number, right? And then this in, and then let's say A, and then let's say the number I used earlier. Right, so it's very confusing. This all looks like code, and we're going to decipher it, right? So this whole thing is a DNS record, right? This is what DNS records, individualized DNS records look like. Now, a record can actually contain more than one row, right? So this is a single row record. It's a name that resolves to a single IP address, right? But a name can resolve to multiple IP addresses. I told you in a few ways. One way is that this record could have two rows in it, and they just resolve to two IP addresses, right? Simple as that. And when you return this kind of multi-record or multi-row response, ultimately your browser or client software, what it's supposed to do is basically spread load 50-50 across these things, right? And most do. That works fine. Another way to go is actually, is what's called weighted round robin or weighted DNS, where instead, your authoritative name server 50% of the time responds with this answer, and 50% of the time responds with that answer, right? And as long as you've got a lot of queries from different places and a lot of different caches and recursive name servers kind of resolving things for you, the laws of large numbers will work out just fine, and 50% will cache this one and 50% will cache that one, and you get a similar effect. Sometimes it can actually be better than returning these kind of multi-row responses, but there are differences, right? Like, so that when you do weighted round robin and you just respond with one row, 50% at a time, well, your client or browser no longer has like a backup choice, right? So if you tell two IP addresses to the browser and the first one goes down, it can try the second, and most will. So that tends to give you better resilience, right? So if your goal is resilience, right, what you really want to do is like, well, I'm in two availability zones or two data centers or two regions. You should just put them all in your answer, right? And then let the browsers try what they can connect to. If they connect to one, great. And if one of your data centers goes down, without even making any changes, right, you'll still get a pretty decent success rate because your browsers will just try the next one for you, right, which is nice and awesome. We do this. CloudFront does this for you if you use CloudFront. Application load balancers do this for you if you use application load balancers. NLBs do this for you if you use NLBs. We just do it under the hood. You don't even have to think about it. When a data center or one of your nodes fails or something like that, you've already got these answers out there, and your client will try the next one, and then we'll actually take the answer out of the rotation just as an optimization as well, because there's no point giving it out if you know it's going to fail, right? So these are what DNS records look like. So this part's the name, right? this part's the TTL, so we covered that earlier, right? So that's how long it's permissible to cache these things for. This in thing here, that's actually called the class, and is called the this is the internet class. Early on in the design of DNS, there was thoughts that maybe DNS would be used not just on the internet, but on other networks and in other contexts, and that it might even be used for things like database queries and so on. And so it was designed with this flexibility. I think there's only one other class defined, which is, or two other classes defined, which is like chaos and Hesiod, I think. And you can basically completely ignore them. Nobody uses them. The internet class is the only show in town. This is always in, right? This over here is the record type. So this is an A record type, which is short for address, right? And then this is the data. Or it's often called OR data, record data, right? And if these are part of a DNS query, this name is often called the Qname, the query name, right? And the type is often called the query type, right? And together, the name or the query name plus the query type, so let's call that the query type, plus the query class, which is pretty much always internet, right, are called the Q tuple, the query tuple, right? And whenever DNS servers are making requests on the wire, right, so like these requests, what's going on is the requester is asking for a Q tuple. It's like, tell me the answer to this query tuple. It has to give all of these things, right? It has to ask, it can only ask with this level of specificity. It has to say, I want to know the A record for the internet class for this query name. Now there is a special query type called Any, and you can and it can, if you set it to Any, it's like having a wildcard, and the question can be, tell me any records of any type that exist for this name, please, right? And gets the answers back that it gets back. So that's what's flying around on the wire, right? The actual Dns wire format, I'm not going to get into too much. It's like a half ASCII, half binary packed wire format that predates even ASN1 and things like that, and is kind of bizarre. It's got this crazy custom compression scheme in it, which isn't even very good, called label compression, where it can share data across what are called DNS labels. And it's just, if you ever want to go deep on how not to build a wire protocol, take a look at DNS sometime. But what is happening on the wire is that these queries are flying around in the form of these query types, and then we're getting back answers, and the answers look like the first thing. The answers include the whole Q tuple, the TTL, and the OR data. The wire format is actually not in the same order that you see in DIG, but you know, there's just, DNS is full of esoteric, weird things like that. All right, so then before we start digging through how queries actually work, one more important detail is that this communication too, right, happens over either UDP or TCP or both, right? So DNS, it's a really old, well-defined protocol. It got a very early port assignment when they were asking for a port. It's on port 53. Right, so like HTTP is port 80, HTTPS is port 443, email, SMTP, that's port 25, DNS is port 53. Right, whenever you're making a DNS query, it's happening over port 53. And typically, what resolvers do is they first try using UDP, that they'll send a request using DNS over UDP, and they may or may not get a response, right? Or they'll get a response that basically says, please use TCP. And then it'll use TCP as a fallback, right? It'll then try over TCP if it didn't work over UDP. And what's going on there is a little funky, but I like to explain it because it's pretty interesting. So the fundamental reason why DNS prefers UDP, right, is because it's cheaper, right? UDP is considered a stateless protocol. So when you send a UDP message, you get to just fire and forget it, right? So let's say we've got our DNS query. We can just send it off into the ether, send it to Recursive Resolver, or the Recursive Resolver can send it to Untitled Resolver, and it just sends it off, and then, okay, well, it doesn't have to buffer it, it doesn't have to promise to retry it. There's a bunch of, it can do that at the application level, but it doesn't have to kind of think about it at the network level, and that's cheaper, right? And than TCP. So in TCP, the way TCP works, TCP has got the state machine built in. Everything that's sent is also acknowledged. And so you have to remember your thing and wait for the acknowledgement. And if you don't see the acknowledgement, retransmit it and so on. That's how TCP gives you reliability and ordering, for what it's worth. But that requires state in the network stack, right? And DNS, they were like going, well, since we have to do retries, and since we have to verify the DNS answers match the query that we sent, we have to, we have to put state anyway in the DNS server. So let's save the state that we would have needed in the network stack. That was kind of the early thinking. And remember, DNS was designed the early 80s, and resources were severely constrained on devices, and it was worth saving every byte. But the downside so that's kind of a good design decision, but one of the downsides of using UDP is that because it doesn't have that reliability, you have to do retransmits or fallback. Now, you would think maybe retransmits would be enough, right? Okay, well, my question didn't get there, or the answer didn't get to me, so I'll just try again. Okay, it'll work next time, right? But it's not actually enough, because there can be network issues where the query is just never going to get there, right? An example of that is when the path MTUs are different, right? So if we draw the internet as a series of buffers, or as a series of tubes, which is actually a pretty accurate metaphor, those tubes are different sizes sometimes, right? And they have what are called maximum transmission units, right? The most amount of data you can send at a time in each tube, right? And typically, it's at least 1,500 bytes, right? But sometimes it's not, because sometimes your tube has overhead and insulation and things that make it smaller than it needs to be, right? And so let's say you send a DNS query. Well, those are pretty small, right? So DNS queries pretty much always get through the tubes. They're generally tiny. But let's say the response is pretty big. Let's say it's got a whack load of IP addresses in it, or a lot of data in it, and it's bigger than 1,200 bytes, right? So what's going to happen is the DNS response is going to get through this pipe just fine, this tube just fine, this tube just fine. It's going to get to this tube, and it's going to, I can't handle that, right? And it's going to send back an error message, an ICMP error message that says, yeah, that was too big, fragmentation required, right? And that error message is going to get back to the operating system, and it's basically not going to really do too much with that. Really modern systems, like ones built in the last 10 years, now know to remember that new MTU, and then the next time you retry, it will lower your MTU that it's sending, and it'll know to fragment the UDP packets a little differently. So it'll take the UDP message that you want, like this big answer, and carve it up into 1,200 byte sized packets that then have to be reassembled at the other end using what are called IP IDs that have to match across those fragments. But that requires state in the networking stack too, right? So this whole thing for a long time was just really unreliable. It's pretty reliable these days, but for a long time it was unreliable. And it you fell into this trap where you really just can't expect large messages to get delivered over UDP. It's too hard. Like I said, these days that's not true, and actually DNS has a mode where you can send large messages over UDP. There's an extension called eDNS 0, and if the client and the resolver say they support it, they can actually send huge messages back and forth over UDP with no trouble and they just, you know, take for granted that the network and the operating systems will figure it out. And that works great. But the more traditional solution was, okay, well, I didn't get my answer over UDP, or I got a response from the name server that basically says, you know, this answer would be too big over UDP, so I'm going to truncate it. I'm going to deliberately make it small, and I'm going to return that to you. And then the DNS querier goes, okay, well, either I didn't get a response, or I got a response that was truncated, so now I'm going to try again over TCP. I'm going to go to you over TCP, and over TCP we can transmit gigs and gigs and gigs of data, right? So we'd never have trouble over TCP, right? So that's why the UDP and TCP are both in the mix, and how TCP fallback generally works. We're not going to talk about zone transfers today. We're going to focus on resolution and recursion, but zone transfers and things like that, which are large, you know, transmissions of bulk data sets, also tend to be TCP and use TCP as they start out. All right, so I said we were going to walk through a query, and I think at this point I hope we've oriented ourselves enough that we're going to be able to follow a full walkthrough. Right, so we're going to look, I'm going to switch to my terminal, and all right, I got to log into, man, my terminal gets super slow when I am Twitch streaming, and I gotta find a workaround for that. I think I need a new laptop is the main one. All right. So, there we go. I've got my terminal set up. Let's see. All right. So is this big enough? Hopefully it is. So first query I'm going to do is I'm going to query for the root zone, right? So dig is this utility that can do DNS queries for you. Like if I do a dig for www.amazon.com, it's actually just going to go through and do everything that I'm about to walk through for me and tell me what the answer is, right? And here we see it is 54.240.172.69, right? That is an IP address for www.amazon.com. But we're going to walk through how, and I actually got that from the Recursive Resolver. Dig's default behavior is to just ask my Recursive Resolver, like, what the hell's the answer, and then figure it out, right? But we're going to walk through every single step. So the first query I'm going to try and do is a query for the root zone, which is called dot, right? So if I do dig dot, that is a valid DNS query, right? So dig's default query type is A, right? Which is tell me the address of this thing. And so we just asked for the IP address of the root zone. Well, the root zone doesn't have a single IP address, right? There's no website dot that you can just go to. That's not what's going on, right? So instead, what's in the root zone are what are called Dns Records, name server records. And, all right, there you can see a list. I'm going to pipe that through less. So here's the current list of root name servers, right? So again, this came from my Recursive Resolver, right? Not from what was in the hints file or anything like that. If I query that again, I get a slightly different answer with a different TTL, probably because I went to a different resolver. So I'm going to pick one of these. Let's say the H root server, right? So this is the list. This is what's in the root zone. It's just this boring list of like, here are the name servers for the root zone, right? That's what it's telling me. Now, if I query one of those root servers directly for the same thing, right? And the way I do that is dig has this @ syntax that lets me query one of them directly. This is what it's telling me. So this is an authoritative answer, right? And actually, if you look at this flags here, there are flags on DNS responses. It's got the AA flag, which means this is an authoritative answer, right? It came from the authoritative name server. Actually, there's some other things. I might as well cover what's in a DNS response header, right? Like, so it's telling us, hey, you asked a question. That's why it's set. It's weird that the response says query, but it really does, because what it basically means is, yes, this is a response to a query, and not like a response to, say, a transfer. There was no error. The query ID. So when a DNS server makes, or when a DNS client or resolver makes a query, it includes an ID, which is just a random 16-bit number. And those have to match, and that's just how queries and responses can be matched to each other when there are multiple queries for the same name. Got to have some way to dedupe them. So this comes back with the same ID, so we know this is the answer to our question. It's got a few flags set. Here it's telling me that we've got the authoritative answer is the one that's important. But it also is telling me that I desired recursion. It didn't use recursion, but I indicated that. And it was a query for a record. And there were 13 answers. Those will be in the answer section. There's nothing in the authority section. And then there's 27 things in the additional section. So that's like this appendix that the name server can respond with. And we'll see why that's important. So it's telling me, okay, here's the 13 name servers for the root zone. They're A through M, root-servers.net. The TTL is really high, right? That's days, a week or something. I don't know. If someone could do the math, go for it. So that's you can cache that answer for quite a while, right? For a very long time. And now the additional section. Right. Recall when I'm bootstrapping, right? It's telling me here's the list of name servers, but how do I know what their IPs are, right? How do I connect to them? Well, the additional section tells me what their IPs are, right? Now in DNS, it's not obligatory that an authoritative name server do this. It doesn't have to tell you the IPs for the names you just queried, unless there really would be no other way to figure them out. Right? Because there can be situations where, well, what happens if the name server is in the zone that you're querying, right? Then you've got the circular dependency like we mentioned earlier, and you have to have a way to resolve it. And the way to resolve it is, well, it will also tell you what the IPs are for those name servers. These are glue records. This is all that glue records are. They are hard-coded answers that are kept in what's called the parent zone, right? So these records are all for like c.root-servers.net. Dot isn't really in charge, like the root zone isn't really in charge of what the value of these IPs should be. Really the zone root-servers.net is, right? That's the dude who's really in charge of what these records are. But to resolve the circular dependency, we're going to include these glue records, which are hints, right? Here's what the IP addresses are for those name servers. And a recursive resolver, typically, there are parent-centric and child-centric approaches to how to resolve glue records, but the most common is child-centric. And what it's typically going to do is going to go, okay, well, great, thank you for that list. I needed that to resolve the circular dependency, but I'm not going to completely trust you on that, so I'm actually going to go to root-servers.net and ask it, are you sure, right? Like, what is the IP of those? So it's going to go and, like, let's say it wants to use c-root-servers.net, right? It's going to want to ask, what is the IP address really for that, right? So if I, so I'm at H, so let's ask it for h.root-servers.net, right? So we're asking the root server name, root server H, what is your IP address, and so on. Oh, didn't get that query right. Oh man. Every time I press up, it just pauses for like 2 seconds. And that, right? So there's my answer. it's telling me the IP address is 198.97.190.53, right? And most resolvers are going to believe that over the glue record if there was a conflict, right? It's going to go, well, the child zone is closer to the truth, so it knows for sure, so that's going to be the one I go to, right? And if we look at our previous answers, once this 2-second pause ends, was that the same one? Let's see. No, it was a different IP. So there you go. All right. So that's how I bootstrap a root zone, right? When the resolver starts, it does this query for NS, tell me the name servers for the root zone, and then it's probably going to do some, follow-up work to resolve each of those root name servers to an IP address, and check that IP address is the right one with the child name server, and just basically build up confidence. But it'll take like a few dozen queries to do all that, right? It's going to do this one query for the root zone, and then it's going to query each of those name servers, and then figure out, well, what do you really think your IP is, and so on, and cache that, right? And then it's going to refresh that every so often. As we saw here, the TTLs are huge, so it doesn't really need to refresh those except every few days or something, right? And it does that once on startup. That is pretty much outside of DNS experts debugging things, the only time an NS query is really used. There is a technique called Cname minimization these days for privacy, but pretty much in normal DNS operations, that's the only time a name server query happens. And a lot of people think name server queries are an important part of how recursive DNS works. It's really not. And I'll show you why in action. So we know a root name server. We might as well start using it by IP just to prove that works. So let's go to H. God, it's killing me how pause every time I press up. What is going on there? It doesn't happen when I'm not streaming Twitch, so it's some weird scheduler interaction. All right, so we're going to query it by IP. We get the same answer, of course, right? So what's happening when your recursive resolver goes to query, tell me the IP address for Amazon.com, is it actually just asks, what's the IP address for Amazon.com to pretty much everything in the way, right? So it starts with a root name server and says, well, do you know the IP address for www.amazon.com, right? So I'm just asking the question section here, tell me the A record for www.amazon.com. And of course it doesn't. Now it could, it's entitled to, right? Like in theory, the root zone could tell you the answer for www.amazon.com because www.amazon.com is under dot, right? And that's the way these things work. There's a concept called bailiwick, where basically anything that's under a DNS hierarchy is in a zone, in the name server's bailiwick, and it's entitled to answer that. But what it says instead is, well, I don't know what the answer for www.amazon.com is, but I do know what the name servers for com are, right? And so it gives them, right? It's like, here are the name servers for .com, which go off to VeriSign servers or whatever, right? And I'm going to just pick the first one because we're going to query that. And you see here it included glue, right? So, it tells me what the IPs are for those. And that's important because we'd have a circular dependency if we didn't do that. And now we're going to go ask one of those what the IP for Amazon.com is. All right. So com doesn't know what the IP of www.amazon.com is, but it does know what the name servers for Amazon.com are, right? And here we see Amazon.com. It's on a mix of Ultra and Dyn. You might be asking, why isn't it on Amazon Route 53? And I've seen that a topic of discussion out there in a bunch of places. And the answer is it is. Amazon.com actually, and as we'll see in a minute, it is on Route 53, and you'll see how we get there. But for a bunch of mostly legacy reasons that, there's just been no reason to make a change at this level, this one little level of indirection is hosted on Ultra and Dyn, and you know, as long as that continues to work, there's no urgent need to change it. But at some point, will probably become Route 53 name servers that you would see here. And so here, you're starting to see something interesting, right? So we're getting told, okay, well, here are the name servers for Amazon.com. But we're not getting anything in the glue, right? There's no glue section this time. We get to the end, there's no glue records, right? And we don't need glue. And the reason we don't need glue is there's no circular dependency anymore, right? UltraDNS.net, UltraDNS.co.uk, Dynec.net, none of those end in com, right? So there's no reason the com name servers would know what those IPs are. And there's no reason it would need to tell you either, right? So at this point, what your recursive resolver is going to do, it's going to pause everything, right? And this is why it's called a recursive resolver, right? This is when the recursion kicks in, is it's going to have to resolve one of these name servers to then figure out what to do next, right? So if we pick one at random, I'm just going to pick the first Dyn one, right? We're going to have to now do everything we just did for www.amazon.com, but now to resolve that name server, right? We're going to have to go back to the root zone, and it's going to tell me, well, I don't know what ns1.p31.dynec.net is, but I do know .net. And then .net's going to tell you, well, I do know dynec.net, and so on, right? And so I'm not going to do that laboriously by hand. I'm going to make Dig do it. So Dig has this option called Dig plus Trace that will basically do all of those steps for me, right? And will show me what's going on. So it goes, first step, it goes to the root servers, right? Got an answer for .net. Tells me the name servers for .net. They end in .net, so we should see some glue. Oh my God, we're seeing some Dnssec stuff going on now at this point. We haven't talked about that yet. We'll talk about that later. But the .net name servers gives me that list. Oh, okay, and then tells me, okay, well, .net then tells me, okay, well, here are the name servers for Dynec.net. Okay, they're these dynamic network services.net and so on, right? Another answer again, all the way down. I can finally ask that name server, okay, what's the IP for ns1.p31.dynec.net? And I get the answer, right? So like 6-7 steps there that all just had to happen by the recursive resolver, right? It had to pause even attempting to figure out what the rest of Amazon.com is just to go do that work, right? And so let's go back and do our original query. So now we can ask one of the Dyn name servers, hey, you're supposed to be authoritative for Amazon.com, so you should know what www.amazon.com is, right? So we go ask it. And it says, hey, www.amazon.com is a Cname. And the data is tp dot, you know, what you see here, 47 blah, 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 .amazon.com. And that domain, blah, 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 frontier, is hosted on Amazon Route 53. There's our Route 53 name servers. By the way, you might notice all of our Route 53 name servers use different TLDs. One is in .net, one is in .org, one is in .co.uk, one is in .com. We do that very deliberately so that if any of those TLDs have outages, Route 53 won't have an outage. And we also use it as part of our management technique called stripes, where we never make changes to any more than one of those servers at a time, ever, just to make sure that, you know, we've got lots of resilience built in. But it's but here I'm getting told it's a Cname, right? And so let's go back to document view in a second. So earlier when we covered Q tuples, right? Names, TTLs, classes, types, and so on. Cname, so we mentioned Annie, which is a special query type that basically says, you know, just tell me any records that exist. I want everything, the A's, the NS's, whatever else you know for a given name, right? Well, Cname is also a bit of a special type. You can ask for a Cname by type, like you can do a Cname query. It's highly unusual, nothing really does that. But Cname is a special kind of response record, really, that basically says every single every single record under this name of any given type, you should actually just pretend the name is this other name, right? And it's short for canonical name. So what it's saying is, you thought the name was www.amazon.com, but the actual canonical name is this 47CF, frontier thing that we just saw, right? And so it's kind of a redirection or indirection or aliasing technique. Now, because Cname, so this is one of the big design mistakes in DNS. Cname is not record type specific. It's not saying, hey, www.amazon.com with this A record should be of this A type is actually over here. It's saying all records of this type, of any type with that name, should go over here, right? And that's unfortunate because it means CNames can't coexist with any other record types for a given name, which basically means they don't work at the apex of your zone. So, which basically means they don't work. They work for www.amazon.com, but a CName doesn't work at Amazon.com level. And if I have to make sure to cover why that is, and we'll go into things like MX and SOA records. So if I forget, remind me in the chat, but I'm going to make a little note here to make sure I cover that. So that's what a CName is, right? Let's go back to the terminal view. So now we need to know, okay, so I'm supposed to query this thing instead. So let's go query this thing instead. So since it's a different domain, I'm not going to do the full recursion. I'm just going to have dig do it. So let's go down here. So it's telling me that the frontier name is a CName to www.amazon.edgekey.net, right? Which I believe is the Akamai CDN, right? Amazon uses multiple CDNs, including CloudFront, but for some things, I believe that's Akamai. For some things, it uses Akamai too, right? So it's saying, okay, that name is also a CName. So we've got like a double CName, right? And then we're going to query that too. Do the same thing. And so you can, like that little dig plus trace there, probably ran 5 or 6 queries just to figure that out. This one will do the same, right? And you can start to see the recursor is doing quite a bit of work, right? It's having to do, quite a number of queries to figure out, okay, well, this is another CName. How much, work it has to do to figure out, okay, well, here's the IP address at the end. Maybe this one will be the IP address at the end. I don't know how Akamai do their DNS setup. We'll figure this out. Yeah, there we go. We got an IP address, right? One of Akamai's nodes, and that's what our web browser can go talk to, and get content from Amazon.com, right? So probably 50 plus queries there from scratch, just to get all the way to figuring out what the IP is, right? And so you might think, oh my God, this seems like a lot of work to ask a recursive resolver to do. Won't this take a lot of time? Isn't this going to slow things down? There's awful lot of myths in there to bust too. It is a lot, but a lot of these queries are cacheable. Second time I do it, it's not going to have to do almost any of this work. The records higher up the tree are even more cacheable than the ones lower in the tree, so you get really, really nice caching effects. But another significant factor is modern resolvers, for the most part, prefetch, right? So they resolve DNS names before you even need them, right? And they look at what TTLs are about to expire, and they go get them before you're going to ever be blocked on it or have to wait on any of this recursion, which is super, super awesome. I mean, Amazon.com is, easily one of the busiest websites in the world. You can go look it up wherever it is on the Alexa 100. And, we've done many experiments and measurements, and it's really hard to make DNS changes stand out in terms of any impact on like browser or client experience. there's just so much caching and redundancy and like Anycast and stuff like that in the DNS system that this stuff just ends up in the noise, in my experience. So we got there in the end. We eventually got to, okay, we figured out all the recursion it took to resolve to an IP address, and now we know to connect to it, right? So that's what's going on. That's the queries and responses that are flying back and forth. Let's get into some more types, right? And what else DNS can do, because there's definitely more, right? So we started off with a query type for the answer, right? So typically these days, modern clients will actually do 2 queries in parallel. They'll fire them off at the same time. One for A and one for quad A, right? And that's where IPv6 records are stored, right? And just like up here, you can have multiple of those, right? And so, you know, typically your operating system and browser and so on will kind of go, well, if I get back well, a lot of the time they just don't get back a quad A record type. It just doesn't exist, right? It's just not there, and we'll do nothing based on that, right? There are let's look at an example of that. So I don't think we have IPv6 on that part of Amazon.com. So let's see what happens there. So there's 2 types of non-existence in DNS. One is you query for a domain that doesn't exist, and you get what's called an NX domain response, right? And that just tells you, hey, that whole domain doesn't even exist. But if the domain does exist, but the type that you queried for doesn't exist, you get what's called a no error empty response. So it's no results, no error. Like, you query for a name that exists, so there's just no records of that type. You just get back an empty response, and you kind of have to infer that it doesn't exist. And that's what happened here, right? We got a 113 byte response that's basically got nothing in it, saying, well, you got the domain right, and here's some details about the domain. I'll explain those in a bit. But that quad A doesn't exist, so there's no IPv6, and then your browser knows, okay, I'm not even going to try connecting to Amazon.com over IPv6. But if it did return an IPv6 record, right, like many of our services and websites do, your browser would probably prefer IPv6 and would try it, right? And if it didn't work, maybe fall back to v4. And since it needs both on hand to do that, that's why it'll do 2 queries in parallel. And you don't need to serialize them, so, you know, just go do it. So those are typically what are in queries. And if you were to look at a resolver's logs and what's going on, 99.9999999% of things are going to be A's and quad A's. And there's really no other queries coming into a resolver. You might occasionally get an admin or an expert debugging things that would send in a manual query that does something else. But pretty much this is what the stub resolvers and application software are asking for. But there are other query types, right? So one, for example, is text. And you can just put text in a DNS name, right? You can just have some arbitrary text there. It's used sometimes for verifying domains. You know, if you're buying a certificate, the CA might ask you to put this secret identifier in a text record to prove you own the domain, right? Things like that. Or there is also there's also a way of putting like hardware info in here. Pretty much nobody uses it. There's but the ones that matter, right? The record types that are probably most useful to know. Well, we saw name server already, the NS record type, which is used to figure out what the name servers are for a particular zone. So that's one we saw already. And we saw SOA, but I didn't explain it. And what a SOA record is, it's the start of authority. And it is what kind of sets up a DNS zone. So let's look at one. I'm going to go back to terminal view. Oh, someone's mentioning the lock record, which is GPS locations. So let's look at a SOA record. There'll have to be some in here. So here's a SOA record for the n0a.akamaiedge.net zone, right? And this SOA record tells you a few things, right? So firstly, it tells you where the zone kind of begins and ends. So it's telling you this zone is for a.akamaiedge.net. That is its own DNS zone. It's going to have its own set of name servers, and it's got its own set of everything. Now, as I mentioned earlier, zones can be delegated. So this dude can say, well, part of my zone, if you happen to be querying for it, I might send you over here. But in general, I'm authoritative for everything, right? And the first field is going to be, well, what is the authority? What is the authoritative name server that has the final say over everything that's in this zone? And here it's saying it's n0a.akamaiedge.net. This is a legacy thing. It was used in when people were doing what are called like open secondary DNS systems and things like that don't really exist anymore. You can more or less put anything you want in this field. Nothing's going to pay any attention to it. The next is, by convention, it's an email address, except the first dot is the @ right? And you can, in theory, email this email address, and they should do something if you need them to about this zone. So it's like, hey, if you have a problem, here's who to email: hostmaster@akamai.com, right? The next is a field. There's basically the serial number for the zone. Anytime you update the zone, you can increment this serial number. You can more or less ignore this field in modern DNS, and unless you're running secondary DNS setups yourself and using like legacy zone transfer protocols, doesn't really matter. And then the rest of the fields are various numbers, but the first one's the most important, and that's the negative TTL. And it defines how long you're allowed to cache the non-existence of an answer, right? So if something doesn't exist, it doesn't have a TTL, right? So how do you know how long you can cache that non-existence for? And that's what this value is, the negative TTL, right? And generally you want that to be quite low, right? Because like, let's say you're creating a new record, like www.amazon.com, right? And you might update the record and press return, and then but before it's had a chance to propagate yet, you might do a query for it. Now if the negative TTL were quite high, you're going to have poisoned yourself, right? That's going to stick in your cache, and your cache isn't gonna go and look for the www.com until that TTL expires. So generally you want that number quite low. But that's what a negative TTL is. For Rule 53, we've paid pretty careful attention to all those values and picked pretty sane defaults. I can't remember exactly what they are, but if you go create a hosted zone on Rule 53, that'll tell you. And then the other another important record type here is MX, right? So MX records are used for email, right? It's how email servers figure out where to send your emails, right? So if my email column at Amazon.com, when someone sends me an email, their mail server has to know, well, what's column's mail server? And the way it does that is it asks DNS, hey, tell me the mail servers for Amazon.com. And it does that with this MX query, right? And then an MX response is this like ranked list of mail servers. They can come and they have a priority. There's like a number. So you can get like MX10, MX20, and that basically means, well, try 10 and then try 20 and so on. MX records, right, typically live at the apex of a zone, right? So there's an MX record at the apex of Amazon.com, right? If we query for Amazon.com, type MX, we'll get an answer, right? That's its MX record. This is why CNames can't really exist at a zone apex, right? Because here's what would happen. You get this weird race condition that crops up in the distributed system. If you had a CName at the level Amazon.com, right? And let's say I did an A query first, right? Let's say I just did an A query and it came back and it said, well, I don't have an answer for you. I don't know what the IP is for Amazon.com, but actually its canonical name is blah, 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 than Amazon.com. So you should just always look over here, right? Okay, well, my resolver would cache that. And then the next time, and then let's say I do an MX query, right? It would come and it would show up and it would do, get to your resolver, and your resolver would go, well, I know that all names, all records that are named Amazon.com of any type should actually go over here to this other name. So this MX is going to get redirected too. And so you just can't really have Cname coexist with any other record type, MX or SOA. And those are both required at the apex, typically. So that's why you can't do regular DNS CNaming at a zone apex. Really, really, really frustrating. Would have been a very simple design change that would benefit most people. So instead, and some people have, that's an easy mistake to make. Some providers have rolled out features where they tried to do CNaming at zone apexes, and then they ran into all of those, distributed caching problems and had to roll back and undo the features. But what we did with Amazon Route 53 and the way aliasing works, right, is we have this alias feature that actually is at the record name type level, and it happens behind the scenes. It doesn't happen in the DNS protocol or on the wire. Nothing on the wire knows it's happening. Just behind the scenes, we know, okay, if a query comes in for Amazon.com type A, actually give this other answer from this load balancer or this CloudFront distribution, because we know it, right? And so that's pretty cool. And but only works when you kind of know all the answers. Like they all have to be on the same authoritative DNS provider, like Route 53, right? It's the downside of that approach. Other record types that you may have seen. So one is Srv Service Records, which are this fancy way to have weighted records that can also specify the ports and protocols that something should connect to. It was an attempt to make how to connect things on the internet together a bit more agile and flexible. Didn't really take off. Ended up being used in a few protocols. Some VoIP protocols use it mostly. Some video conferencing protocols use it, but Srv is not terribly popular outside of those contexts. PTR records, which are for reverse DNS, which we didn't really talk about, but there's basically some magic in reverse DNS where DNS can also translate IPs into names, right? So if I've got the IP address 192.0.2.1 and I want to find out what the name of it is, then there's a convention to basically, just turn it around backwards. So 1.2.0.192, and then put this domain after that. Inadder.arpa, right? And resolve that with type PTR, right? And that's going to be the query. Everything else is going to be exactly the same as we covered earlier. It's going to resolve this just the same way we would have resolved an A record. And then it'll get an answer from an authoritative name server for the 2.0.192.inadder.arpa zone that says, well, here's the name. It's, www.amazon.com, say, right? And that's how we do everything in reverse, right? We're just kind of flipping the system on itself to get things out of it. If you want to use dig to do that, you can do dig-x and then the IP address, and then it'll do all that work for you and figure that out. All right, so what haven't we covered? Covered quite a lot, and we've gone pretty deep. So I'm going to pause for a minute. I'm going to take a look through all the questions and see how we're doing. And if you've got more questions, now's the time to think about it, because probably going to wrap up pretty soon. Great, not too many. So I already answered the resolve.conf question that came in earlier. Did I know that Amazon.com renders a blank page? I did not know that, but that doesn't surprise me. Oh, I see Dnssec. I'll answer that now. Weird custom compression schemes. Yeah, they are weird. DJB, who wrote his own DNS server, Tiny DNS, and DJB DNS, famously called it sophomoric compression protocol, like as if it was written by a sophomore. You know, I don't know what to tell you. Okay, we explained how alias records work. Centryism makes a good observation that COM is dependent on net, given that that all the COM name servers are using .NET names. That is true. And I've always wondered why they don't just put them in COM and just rely on the glue, but it is the way it is. Maybe they get better cache hit ratios if they share the same names between COM and net. Who knows? All right, Dnssec. So I didn't really cover Dnssec. And the reason I didn't cover Dnssec, it could get pretty complicated in its own topic, but I'll try to do it in brief. And the whole video will get uploaded after the stream. It'll be on YouTube as well. It's I have impolite things to say about Dnssec, which I'll probably keep to myself. Dnssec is short for DNS security, and it's a mechanism to add security to the DNS system, right? In my opinion, it doesn't really earn its keep and adds more problems than it solves, and does not provide you with very much security at the end of all that. But that is my personal opinion. At the same time, we fully support Dnssec here. We have an implementation in Amazon Route 53 that people can use, and is awesome. Put a lot of hard work into it. But let me start with a few things. So firstly, you might think something called DNS security would give you privacy and confidentiality. It does not. It does no such thing, which is unfortunate. So it doesn't give you the kinds of security that like HTTPS and TLS and SSL do. It doesn't encrypt your queries or anything like it. And so your ISP or other folks that are interested on the internet can still see what domain names you're going to, right? And if you're going to a domain name that you wouldn't like somebody necessarily knowing, Dnssec has nothing to help you, right? Which is pretty bad start. So as I said earlier, there are alternatives that help you there, right? So you can have privacy between your Stub Resolver and your Recursive Resolver by using, say, DNS over HTTPS, or DNS over TLS, or DNS over QUIC. And that will give you encryption between here and there, right? Doesn't give you much more than that. Your Recursive Resolver still gets to see what you're querying, and your network up there might also be able to infer just by seeing timing. Well, you just made a DNS request, and then this guy just made a DNS request, so that was probably the one you made, right? And so it's not terribly amazing privacy. Apple have announced, or now they've launched, I guess, a pretty cool DNS Privacy Technique in their latest version of iOS, at least, and I think other OSs, that is pretty cool and uses a pretty cool scheme where they split responsibilities, and the Recursive Resolver can no longer see who's querying what, because there's some clever intermediaries and so on. But like, the best we have in terms of DNS privacy is still not end to end. It's basically between you and a Recursive Resolver, and that's about it. And that's true DNS over HTTPS or similar, not true Dnssec, which does literally nothing for you on that front, which is sad. The other sad thing about Dnssec is in the world of attacks on DNS, we didn't really talk about attacks, but there's some ways in which DNS can be attacked. The most common is DDoSes. DNS is often used as part of DDoS attacks, both as a target and as kind of an aid in DNS or in DDoSes. It's used as a target of DDoSes because, DDoSers can just send huge amounts of queries to DNS servers to try to overwhelm them. And if they do overwhelm them, the domain is going to stop resolving and they're going to have an outage, right? And if the DDoSer is trying to vandalize or extort a victim or whatever, that can be effective, right? Now we have very sophisticated DDoS mitigation techniques here. Many other providers do too. So in general, it's the kind of thing that's taken care of by large providers. But DNS as a system, is certainly open to attacks like that, right? And Dnssec does nothing for DDoS attacks. In fact, it makes DDoS attacks much worse. It makes queries more expensive to serve, right? Which makes those DDoS attacks worse. And actually, DDoS attacks can be enabled by DNS and Dnssec too. So another thing about UDP is, right, because there's no handshake, as in TCP, where you send a SYN, you get a SYN-ACK, you send another, and so on. UDP, you just send a message. For networks that don't enforce, anti-spoofing measures, those networks can be sources of just huge amounts of spoofed traffic, right? And so if an attacker has access to one of those networks, or botnet or whatever, they can generate these spoofed DNS queries that come with that actually use the victim's IP address as the source, right? And they'll go to a DNS server, and the DNS server will go, here's your answer, and all those answers will go to the victim, right? So the DNS server can be used as a reflector, right? And in traditional DNS, answers were pretty small. There were no bigger than the queries, right? So the attacker didn't get much benefit, right? But once Dnssec came along, the DNS answers had to have all these keys in them, right? And became much, much bigger than the question. And so Dnssec would be used to aid those reflector attacks. So the attacker would send these cheap, tiny messages with the victim's IP address, and the DNS servers would respond with these huge payloads of responses that include all sorts of Dnssec material to send to the victim, right? And so that's how Dnssec, in my opinion, actually lowered the real-world security of the DNS infrastructure, and has been just a bad idea. But what Dnssec does do, right, is, well, there's this old school problem with UDP where since anybody can forge or spoof these packets and responses in theory, what's gonna stop somebody from just sending back a forged answer, right? And the answer is not much. There's a 16-bit ID in the answer that has to match the question, and that's about it, right? That's not much entropy. And so by forging 65,000 responses and sending them in a very small amount of time, you can be almost guaranteed that one of them will match, right? And you can get a false answer into a DNS server's cache, right? So that's old school attack. Now modern resolvers just have all sorts of other mitigations against that. Starting with, well, the networks are actually pretty well secured from source spoofing in the first place. Then the next one is they will often use a technique called case matching, right? So they'll vary the case of the query, right? So they'll do uppercase W, lowercase w, uppercase W, like kind of at random, right? And then they'll see if that matches too, and that gives you additional entropy, right? You get one more bit of entropy for every character you can do that with, and that can be quite effective. And most name servers know how to match names like that and so on. And then the other thing they can do is vary the port of the query and response, right? So it used to be that the port would be quite predictable, and a lot of operating systems and software, with the important exception of DJB, who, to his credit, did predict that this would be an issue. Because that port was predictable, you didn't really have to guess it as part of the attack. But everyone learned to make that port unpredictable, to randomize it instead. So between the port being unpredictable, which gives you another 16 bits of entropy, right? So you've got about 16 bits of entropy from the port, 16 bits of entropy from the query ID, and now additional entropy from casing. You actually get into pretty decent amounts of entropy, like 50 bits plus, right? Which you're well into numbers now. You can't just generate packets that send that, right? So that's why the internet isn't collapsing, even though no one's really using Dnssec, right? Like that, because that stuff works, and we've engineered a solution. But Dnssec was like, yeah, that stuff looks a bit pokey. So let's instead cryptographically sign the answers, right? So that they can be truly verified, right? Which is a good laudable goal. Any credible attempt at DNS security should include, end-to-end secure answers. It should just also, in my opinion, include confidentiality and not make DDoSes worse, and all sorts of things like that. But that's what's going on, right? And so in Dnssec, to do that zone signing, there's a few things going on. Basically, in addition to that hard-coded set of IP addresses, there's a hard-coded set of root signing keys that just everybody knows that sign the root zone, right? And then each zone gets to sign their delegations and say, well, when I tell you what the name servers for com are, I'm going to sign that with my key, and you can verify that. And I'm also going to tell you what com's keys are, and that happens recursively. And then com signs its response with its keys, and so on. And all the way down, and you can validate all the way to the end. There's a few little wrinkles with that. One is, well, how do you know the non-existence of something? You can't just sign, well, this thing doesn't exist, because, well, firstly, you don't know what queries are going to come in that don't exist, right? There's like an infinite set of those, and you can't sign them all in advance. And Dnssec wanted to support offline signing, where the key isn't necessarily on the server, right? So if the server is compromised, it's not just game over. So instead, there's this system called Nsec, where basically you create this, lexicographically ordered list of all the records in the zone, and you sign their adjacencies. So you say A and C are adjacent, and I'm going to sign that. And if a query comes in for B, you get that response that says A and C are adjacent, therefore B doesn't exist, right? And that's how that gets validated. Now, challenge with that is, now the zone becomes iterable. It's trivial to take an Nsec tree and just walk the zone and say, well, A and C are adjacent, so A exists, C exists. Now let's go again and see what C is adjacent to, and so on. And you discover the entire contents of the zone. And, the folks behind Dnssec were like, well, DNS is public data, so who cares? Like, it's fine. You can see all this on the wire anyway. But, a lot of enterprise folks were like, what are you, crazy? No, lots of my DNS is internal only, screw that. I'm not using this thing. And so a few solutions were invented. People would first, insert like canary records that don't exist. So instead of saying A and C are adjacent, it would be like, well, A and B are adjacent, even though B doesn't really exist. And B and C are adjacent. So you couldn't completely if you walk the tree, you would get lots of things that actually don't exist. And then, but then the other approach was Nsec 3, where instead of just the records being adjacent, we instead hash them 3 times, and then walk that adjacency of the hashes. And so when a name comes in, you have to hash it a bunch of times and then see where it would fall in the hashed list. Gets a bit hairy, but it does work. It's still iterable in some senses. You can try to reverse those hashes for common names. It's just like password brute forcing. You can also count how many things are in the zone still, even with Nsec 3. So that's got its challenges. And then another wrinkle in Dnssec is it's incredibly brittle. And because DNS is such a low-level system where people aren't really exposed to like error codes and UIs and so on, it's very hard to make changes, right? So when the cryptography needs to be upgraded to go from a very small RSA key, like a 512-bit RSA key, which some DNS servers were using not too long ago, how do you get everybody to stop doing that? Well, it's not like browsers, nowhere near as easy as like browsers can enforce, web servers to say, hey, you have to stop using SSLv3, it's insecure. We're just going to give the user warnings if you even try. And there's going to be this strong incentive for the web server operator to update their protocol. It's much, much harder in DNS because this stuff is buried in configurations no one really understands. And what happens is, well, someone goes and tries and they goes, okay, I'm going to update to like a 1K key or a 2K key. And then they find out, oh, this resolver over here doesn't support that, doesn't work. And then you got to roll back work with that provider and so on, and it's just tremendously slow, like 10 years plus often, to get those changes through the system. It just hasn't been able to keep up as cryptography has evolved. And so the keys that are typically used in Dnssec today, they're just vulnerable to, papers and attacks published years and years ago at this point. And it's just kind of languishing. At the same time, while they haven't had much technical success or, on these sides of things, or really established a great community of people who are improving it and refining it and keeping it up to date, there has been success from vendors getting Dnssec made part of, compliance programs and convincing regulators, oh, it's got security in the name, you should support it, and you should have this as part of your regulatory compliance scheme and so on. And so, folks are having to adopt it anyway for that reason. If you get the keys wrong, if you screw up how you're signing things, you'll have an outage. That's by design. That's what Dnssec is supposed to do. So as people adopt it, it's pretty critical to get all that stuff right. And that's why we support it, right, on Amazon Route 53. Take all that complexity out of the equation for you as much as we can, and help you run it a bit better. So that's my shortish, least ranty synopsis of Dnssec. Someone mentioned happy eyeballs. Doesn't really relate to Dnssec or DNS, but let's cover it anyway. So I talked about, the browser will resolve both these in parallel, the A and the quad A. What the happy balls algorithm then says to do is we'll just try to connect to both in parallel, or maybe give IPv6 a very short head start, like a millisecond or something, which is imperceptible to humans, but enough to just give it a better shot. And then whichever one works, right? But that way you don't have to wait. So when I said earlier about the retries and stuff, Shahil's pointing out the happy eyeballs is more common, and actually that is the way to go there. Whew. All right, that was like an hour and 47 minutes on DNS. Am I aware of any organization that's managed to deploy Dnssec correctly on their first try without failing out of all the validating resolvers? I'm sure some have. I'm sure there are definitely cases where people have. There's TLDs that have adopted Dnssec and managed to not have outages. They really paid very careful attention and got everything right, and they've been. It is doable. Just think it takes a pretty elite team who really understands it. Nowhere near as easy as it is to use TLS certificates. Oh, and remember, right, like if DNS is spoofed, if somebody does manage to get the wrong IP address into the DNS system, that's bad, right? But like, they don't have the TLS certificate. The browser might go to that IP address, right? And I talked about just how hard that attack is in modern things. It's not really feasible in my opinion. There can be other attacks that might work in the DNS system that can lead to, but the cache poisoning one, not so much anymore. But okay, so they get the wrong IP address in there. Well, the browser's still gonna warn the user. And these days, with no real way to override easily on the user's behalf, hey, this isn't the legit website. They don't have the certificate for that website. So you've still got that protection at that level. And that's another reason why Dnssec just really isn't as important as kind of when it was being invented. So we'll see. I'd love to see a secure DNS protocol. We'll see. I think one of the other great mistakes in the DNS protocol is it's short for the domain name service, right? But wouldn't it have been cool if it was short for the DNS name service, right? Because then it would be recursive. And it's a protocol that's all about doing recursion. I think that's a very meta, kind of crazy, cool thing, and a bit weird kind of miss. But anyway, all right. I think we're out of questions. This will be on Twitch for 16 days. It'll be on YouTube at some point when I upload things. I have to edit them every time a bit. That's everything I have. If you've got other detailed questions on Dnssec or DNS or anything I've covered here. Twitter is probably the best way to get them at me. Thanks everybody for watching. Come back next week. YouTube, the channel link is on Twitch, but it's the Shuffle Sharding channel. You can go to my website, shufflesharding.com, and there's links there too. I don't know what I'm going to cover next week. I might do a Twitter poll. The two other topics I had suggested for this week was the basics of a CPU pipeline, like how caching works, prefetching, branch prediction, speculative execution, that kind of stuff. What the mental models are for that, how to, think about program efficiency at that level, because I see a lot of people get confused by that, and I think it's easier than it seems. And then the second was functional programming in C, which is all about taking the best aspects of functional programming, which is not very much, and how to apply them to a very non-functional programming language like C. I've got plenty of examples because I've had to have done that a lot. Anyway. Thanks again, everybody. Thanks for the thank yous. I'll see y'all soon.